Good morning. Today I want to show you how to do the braking distance activity. The first thing you'll do is you'll click on this URL and it'll bring you to the simulation. You can set the initial speed for whatever you want. I set it for 35 and you hit start, and as soon as you see a car enter the screen, you hit stop. I messed that up, so let me try that again. Perfect. So you can see my reaction time was 0.2 seconds. That means that 0.2 seconds after the car came onto the screen, I clicked the button to stop. And in that time, the car had driven 10 feet. And it did that before it hit the brakes, so that was moving at constant velocity. And then it took 2.23 seconds for the car to slow to a stop, and that was 57 feet. The total time between when the car came into the screen and it stopped was 2.43 seconds, and the total distance before stopping was 10 plus 57, so 67 feet. I'm going to bring all that information over to my worksheet. So scrolling down here, I know my initial speed was 35 miles per hour. I know my reaction time was 0.2 seconds. And during that time, the car drove 10 feet. My braking time was 2.23 seconds. And during that time, the car drove 57 feet, making the total time 2.43 seconds and total distance 67 feet. Now, unfortunately, this simulator is not using metric units, and we need to use metric units in physics, so I'm going to have to do some conversions. So 35 miles per hour. The first thing I'll do is get out of miles and go to meters, and I can see the factor over here that 1 mile is about 1609 meters. Now I want to get out of hours, and I'll go to minutes, and then I'll get out of minutes and go to seconds. So 1 hour is 60 minutes, and 1 minute is 60 seconds. And when you put this all in your calculator, 35 times 1609 divided by 60, you'll get 15.6 meters per second, or to two significant figures, 16 meters per second. We should also convert the feet to meters, so I'm going to do factor label 3 times right here. 10 feet, and the conversion factor is that 3.28 feet is equivalent to 1 meter. And so this comes out to be about 3 meters. 57 feet using the same factor gives me 17 meters. And 67 feet gives me 20 meters. And it should make sense that these two added together give me the 20 meters I have down here. So let me copy these back up here. 10 feet was 3 meters. 57 feet was 17 meters. And 67 feet was 20 meters. So let's determine the average speed of the car during the reaction time. So that was the time before I hit the brakes, where the car was moving at a constant speed. So I know it had driven 3 meters before I hit the brakes, and I know it did that in 0.2 seconds. And I want to find that average speed. So V equals D over T. I'll put in 3.0 meters in 0.2 seconds. And my speed turns out to be 15 meters per second. Now notice it's a little different than what we got up here when we just converted our 35 miles an hour. We got 16 meters per second. But really, this time here of 0.2 seconds is only good to one significant figure. We can't expect a super accurate answer for the average velocity here. Next, determine the acceleration of the car during the braking time. So for that one, we know we started with that initial speed of 15 or 16 meters per second. I'm going to take the 16 meters per second I got up here. It would be all right if you used the 15 that I got here. It doesn't make too much of a difference. And it comes to rest in that braking time of 2.23 seconds. And we're looking for the acceleration. So with this given information, I would use VF equals VI plus AT. 0 meters per second equals 16 meters per second plus A times 2.23 seconds. A would turn out to be negative 7.2 meters per second squared. So now graphing this. If I make my time axis 0, 0.5, 1, 1.5, 2, and 2.5, 5, 10, 15, 20. For the first 0.2 seconds, which would be over here, the car is constantly going 15 meters per second. And then by 2.43 seconds, we've stopped. And so I'll just take a straight line. I think I could do that with a tool over here. And drop it from here to here. And that would be my velocity versus time graph, or my speed versus time graph. My position versus time graph, I'll use the same time axis. And my position, I'll go 5, 10, 15, 20, and that should be fine. I know at 0.2 seconds, I had gone a distance of 3 meters, so that would be right here. And I know that at 2.43 seconds, I had gone a distance of 20 meters, so that would be right here. Now the way I connect these, constant velocity on a position time graph should be represented by a straight line, so I'll connect these with a straight line. But as I was decelerating, I got to draw a curve, and the curve should have a smaller and smaller slope until at this point the slope should actually be 0. So those are the answers to the lab. I hope you did well.